Hello everyone. Today I am going to explain about the switching power reduction, next the short circuit power consumption and the leakage power consumption. Okay, so here if we consider the equations what we got in the previous discussion about the switching power, that is P average is equal to alpha T multiply with C load VDD squared and clock frequency F. Okay, or we can have P average is equal to summation of I is equal to 1 to number of nodes alpha Ti Ci Vi multiply with VDD F clock. Okay, so these two are the equations. So from these equations we can have one conclusion that so the average dynamic power is directly proportional with the number of nodes or the node transformation factor. Okay, next one is the capacitor load capacitance and the power supply and the clock frequency. So all the parameters whatever we have in this equation are increases the average or the dynamic power consumption, average dynamic power consumption, because all are directly proportional. Okay, so now we'll go with what are the methods to reduce this one. So if you consider this equation, if you reduce any one of these parameters, whatever we have alpha T, C load and VDD squared, and at the same time clock frequency, so we can reduce the average dynamic power. Okay, but here we have some problems. If we consider the clock frequency, so if you increases the clock frequency, what happened here, there will be increasing in the power consumption. Okay, but if you decrease the clock frequency, the speed will be reduced. Okay, it will affect the performance of the corresponding circuit. Okay, so that's why we don't increase or decrease the clock frequency. Okay, next here we have the average switching power dissipation expressions of CMOS logic gates suggest that we have several different means for reducing the power consumption. These measures includes reduction of the power supply. Okay, that is voltage VDD. Next one is reduction of the voltage swing in all nodes. Okay, next one is reduction of the switching probability, reduction of load capacitance. So any one of these, if you reduce, what happened here, the average dynamic power will be reduced. Okay, so now the switching power dissipation is also a linear function of the clock frequency, but if you decreases that one, what happened here, the speed or performance of the circuit will affect. That's why we don't go with the clock frequency. Okay, next one is the best method to decrease this average power reduction, that is average dynamic power reduction or switching power reduction, is nothing but by reducing the power supply voltage. Okay, that is the main important method we have. The reduction of power supply voltage is one of the most widely practiced measures for low power design. In particular, we need to consider that reducing the power supply voltage leads to the increasing the delay. So without increasing the delay, we have to take the measures to reduce the power supply voltage VDD, so to reduce that average power consumption, average dynamic power consumption. Okay, so this is what here, how we can reduce, what are the methods to reduce this dynamic power consumption. Okay, now next we will go with the short circuit power consumption. Okay, so here this is the second one of total power consumptions, that is the short circuit power consumption. So the name itself, it is there, short circuit. Okay, so what is that short circuit means? If you consider suppose an NMOS inverter. Okay, what happened at a particular point, I explained about the CMOS inverter circuit. Okay, there we have considered a diagram like this. It is the current that is flowing in this inverter circuit, as I have indicated like this. Okay, so here this is the current what we have, and the current will be maximum in this region. This is the third region. So here we have like we have divided 1 2 4 5 like that. I have divided the diagram and I have explained that at this point there will be a both NMOS and PMOS transistors will be on condition. Okay, so because of that the more amount of current will flows, that's why the graph will be like this. Okay, so there will be some relation is there for the diagram and this short circuit power consumption. Okay, so here what is that? At a particular point, at a particular voltage, what happened is at an incidence, there will be NMOS and PMOS, both will be goes into the on condition. Okay, so at that point, both will be on condition means what happened here? If this PMOS and NMOS both are in on condition, so there will be a current flow between the VDD and the ground. Okay, that is nothing but and at the same time, instead of charging this load capacitance, the more current will flows between the power rails. The power rails means here VDD and VSS. Okay, so this is called as what? Short circuiting of this VDD and ground. Okay, so because of that, the current will goes from VDD to the ground. So that is called as what? The short circuit power consumption. Or here the power or the energy will be drawn from the VDD or power supply to the ground. Okay, instead of charging this load capacitance, there will be a flow of current is taking place between VDD and ground. So this type of power consumption is called as what? Short circuit power consumption. Okay, so here I have considered to explain that short circuit power consumption, this inverter circuit, right? So if a CMOS inverter or logic gate is driven with input voltage waveforms with finite rise and fall time, both the NMOS and PMOS transistors in the circuit may conduct simultaneously for a short amount of time during switching. Okay, that's what I told. Okay, at a particular point, there will be both NMOS and PMOS transistors will be conduct simultaneously, and therefore, because of that, there will be a short circuit established between, or the direct current path will be established between the power supply VDD and the ground. Okay, so that's what here we have. This arrow mark indicates there will be a current flow, short circuit current flow between VDD and this ground. Okay, the current component which passes through both the NMOS and PMOS devices during switching does not contribute the charging of the capacitance. Instead of doing the charging of capacitance, so what the current will do means direct path established between this VDD and ground. Okay, so that is called as what? The short circuit current component. Okay, for a simple analysis, consider a symmetric CMOS inverter, and the time average short circuit current drawn from the power supply is, so that I average is equal to short circuit current, or I average short circuit. Average short circuit current is equal to 1 by 12 K tau F clock by VDD minus 2 VT whole cube. So this is the average short circuit current. And if you consider the power supply or power consumption, average power consumption of short circuit power consumption, so that equation is equal to 1 by 12 K into tau F clock VDD minus 2 VT whole cube. Okay, so here what we will consider is Kn and Kp are both are equal, and at the same time the tau p and tau n also we will consider as the equal values, so that we will calculate that average short circuit current component or the power consumption we will get is these equations. Okay, now the short circuit power dissipation is how we can reduce this. Okay, the short circuit power dissipation can be reduced by making the output voltage transition times larger, and or by making the input voltage transition times smaller. Okay, either way we can reduce, by both ways we can reduce. The first one is what? The output voltage transition time, we will make that one as larger, or we can make that input voltage transition times will be smaller. So that because here if you observe this one here, tau is nothing but the transition time here. If you reduce that input transition time, automatically this average value will be reduced. Okay, so this is about the short circuit power consumption. Okay, now we'll go with the next one, leakage power consumption. Okay, so here what is leakage power consumption means, if you consider a PN junction diode. Okay, if you consider a PN junction diode, when it is in reverse bias, what happens? Okay, so I will show the diagram here. If you consider a PN junction diode, it is connected like this. So here we have the depletion region, and this one is the P and this one is the N. So if you apply the reverse bias condition here, so that is reverse bias means positive voltage terminal is connected to the N and negative is connected to the P. So because of that, what happened? There will be a increasing in the depletion region. So because it is in the reverse bias, okay, but there will be a flow of current is there, that is reverse saturation current, or we can also call as leakage current. Okay, so here it is negative and it is positive. So the holes in this one is the majority carriers are what holes, and the electrons are the minority carriers. Here, because of this negative potential, what happened? So these minority carriers, electrons will move from p type to n type, and here the holes are the minority carriers. Due to this positive repulsive forces, they will move towards the p and they will cross the junction, and there will be a formation of the reverse saturation current. So okay, so whenever, what is that means here leakage power consumption reverse saturation current means it will be obtained whenever the device is in off condition. Okay, either it may be a PN junction or it may be a transistor. So whenever the transistor or the PN junctions are in reverse bias condition or in the off condition, there will be a formation of leakage current or reverse saturation current. Okay, similarly here we have in our CMOS VLSI circuits or MOS transistors, we have the leakage current or the reverse saturation current that will flows. So if you consider a NMOS transistor, if you consider an NMOS transistor, it consists of if you consider an NMOS transistor here, it consists of source and drain, and there will be a formation of depletion regions between, this is the N substrate, okay, sorry, this is the P substrate. Okay, so this one is the N-type material and this one is also N-type material, so both junctions will be formed. Okay, so if you consider this one, whenever there will be a reverse bias or off condition of this MOSFET, what happened here? There will be a reverse saturation current will flows. That current is called as what? Leakage current. Okay, and another power consumption that will added to this leakage power consumption, or we can also call as reverse saturation current, is nothing but sub-threshold current or sub-threshold power consumption. We'll see both this reverse saturation current and at the same time the sub-threshold current, both will be included in this leakage power consumption. Okay, so we'll see one by one that those two, right? So in a CMOS VLSI chip containing a very large number of transistors, those currents can contribute to the overall power dissipation even when the transistors are not undergoing any switching event. What does that means here? Here our VLSI means millions of transistors will be placed on our silicon area or a chip. Okay, silicon chip. Due to that, all the transistors, large number of transistors, so those currents can contribute to the overall power dissipation, because even though they are under non-switching, that is our switching event undergoing not, even though they are not undergoing any switching event. Switching event means a on and off condition, on to off and off to on conditions. Even though they are not going with that conditions, so there will be a power consumption. There will be a power consumption will takes place in each transistor. That power consumption also we will consider to the total power consumption. Okay, so here we have two main leakage current components in our MOSFET. That is what reverse diode leakage occurs when a PN junction between the drain and bulk of the transistor is reverse biased. That's what I told now in the previous discussion, that if you consider that NMOS transistor, in that NMOS transistor we'll have P substrate and N type source and N type drain. Okay, so between this bulk or the substrate P substrate and the N type material, there will be a formation of junction will takes place. Those junctions, whenever they are in reverse bias, automatically there will be a flow of current that will takes place, that is reverse saturation current. That current is called as what? Leakage current here. Similarly, there will be a formation of junction between N well. If you consider the CMOS process can be, or CMOS inverter can be, or CMOS circuits can be fabricated by using what? N well process or P well process, or twin-tap process. Any of that, if you consider N-well is there. N-well means there we have the P-type or P MOSFET. We will place that one in this N-well. So I will show that one here. So if you consider this, if you want to go with the N-well process, so we'll consider here P substrate or bulk. But here to form the PMOS transistor, we will consider N-well. Okay, so here this N-well will act as a substrate here. So this is N-well, and there will be, and this is the source, and this one is the drain. Okay, so this one is the source and this one is the drain. Both are of what? P-type materials. Between this P-type material and N-well, there will be a formation of the junctions. So whenever these junctions are in reverse bias, or whenever this PMOS transistor goes into the off condition, then there will be a reverse leakage current will flows. Okay, so because of the junctions that are present between the source and drain and the substrate, at the same time the source and drain and the N-well, they will cause the leakage current for us. Okay, whenever those junctions between this drain and substrate, or we can also call as source and N-well process, then there will be a reverse saturation current will flows that causes the leakage power consumption for us. Okay, so these two are the important leakage currents what we have in a MOSFET. Now we will consider an example of an NMOS inverter. In a CMOS inverter with a high input voltage, the PMOS transistor is turned off. There will be a reverse potential difference of VDD between its drain and the N-well, causing the diode leakage current, what I have told here. Okay, so next one is the N-well region of the PMOS transistor is also reverse biased with VDD with respect to the P substrate. Therefore, another significant leakage current component exists because of the N-well junctions. Okay, so if you consider this one is nothing but the CMOS inverter we have. Okay, so CMOS inverter and that too N-well process. So N-well process means in this N-well we can form a PMOS transistor, and in this on this substrate we can form an NMOS transistor. Whenever, if you consider an inverter circuit here, an inverter circuit like this PMOS inverter, CMOS inverter. So this one is the NMOS transistor. One second. So this one is NMOS transistor and this one is the PMOS transistor, and this is VDD. Okay, and this one is VSS, or we can also call as ground. If you apply Vn is equal to 0, so what happened here? This transistor will be on condition, so this will be in off condition. So whenever this NMOS is off condition, so there will be a reverse saturation current will flows in this between this P substrate and the N junctions. Okay, so like that, whenever if I apply Vn is equal to 1 here, okay, what happened here? This one will be goes into the on condition. This one will goes into the on condition, and this one will goes into the off condition. If whenever Vn is equal to 1. Okay, so at that point through this PMOS transistor there will be a leakage current will flows. Okay, so this is about how the reverse leakage current will flow in CMOS, and at the same time in CMOS inverter circuits or the CMOS gates. Okay, so that's what I have given in these 2 points. Like in a CMOS inverter with a high input voltage, the PMOS transistor is turned off. There will be a reverse potential difference of VDD between its drain and the N-well, causing a diode leakage through the drain junction. Okay, similarly, whenever a PMOS is on condition and NMOS is off condition, so there will also we will consider a leakage power consumption. Okay, so that is what here we have the reverse leakage current, right? So a similar situation can be observed when the input voltage is 0 and the output voltage is charged up to VDD through the PMOS transistor. Then the reverse potential difference between the NMOS drain region and the P-type substrate causes a reverse leakage current. Both ways, what I have explained by taking that diagram, Vn is equal to 0 and Vn is equal to 1. at the both conditions. At one time the PMOS will be on, and at the one time NMOS will be on. So whenever these two, that is PMOS is off, there will be a power consumption takes place, that is leakage power or leakage current will flows. At the same time, whenever the NMOS is off condition, also there will be a leakage current will flows. Okay, so these two contributes the leakage power consumption. Okay, and here we have the formula for the reverse leakage current of a PN junction expressed as I reverse is equal to A into JS e power q by V bias by KT minus 1. Here A is nothing but the area of cross section, and JS is nothing but the current density, and e power q is the charge of the electron, and biasing voltage is V bias, and K and T. K is the Boltzmann's constant, and T is the temperature. Okay, so this is what reverse saturation current or reverse leakage current that will provided by these PMOS and NMOS when they are in off condition. Okay, now we'll go with the sub-threshold current. What is this sub-threshold current? Generally, what if you consider V in, okay, so if you consider V in or the gate to source voltage, so I will consider here the PMOS transistor or the diagram of inverter circuit. So if you consider this, okay, this is VDD, and this one is nothing but ground. So whenever if you apply Vn is equal to 0, okay, Vn is equal to 0 means what? This NMOS will be completely off condition, okay, and this PMOS will be on condition. Whenever Vn is equal to 1, so what happened here? This one will be goes into the off condition. This will be goes into the on condition. Then when we are getting this threshold voltage, sub-threshold current component is nothing but if you apply a threshold voltage or the gate to source voltage that is greater than, that is what, if you consider for an NMOS transistor, if V in, or we can also consider as VGS is greater than V threshold voltage of NMOS transistor, VTM. Okay, so what happened here? Vn is in, or the gate to source voltage is greater than the threshold voltage of NMOS transistor, then the NMOS will be on. Okay, the NMOS will be on. There will be a inversion layer will form. That is, inversion layer is nothing but the channel formation will take place whenever the input voltage is greater than the threshold voltage. But and the transistor we can consider the on condition. But whenever if Vin is nearer to this threshold voltage, or Vn is nearer to VTN, Vn is close to the VTN, then there will be a current flow will take place, even though there will be a less amount of channel inversion takes place, not completely. Okay, but the transistor partially conducts. Okay, for this condition, if you consider Vn is equal to 0 or negative value, so there is no problem, because the NMOS transistor completely goes into the off condition. Okay, and at the same time, if Vn is greater than VTN, so the NMOS transistor completely goes into the on condition. So there is no problem with those 2 points, but the problem is whenever the input or the gate to source voltage is approximately, or it is nearer to the threshold voltage of the transistor, then there will be a problem, because the transistor will conduct partially. There will be a small inversion layer will form between the source and drain due to that voltage. Okay, because of that, there will be a current flow. That current flow is called as what? Sub-threshold current. Okay, whenever the transistor is completely on and off, there is no scope of the sub-threshold current. But if the threshold voltage, if the applied voltage is nearer to the threshold voltage, then there will be a problem. That problem is called as what? Sub-threshold current, because the transistor will on partially and it will conduct. Okay, so that's what the sub-threshold current means. Another component of leakage current in CMOS circuit is the sub-threshold current, which is due to the carrier diffusion between the source and drain regions of the transistor in a weak inversion layer. So when this weak inversion layer will form, whenever that input voltage or the gate to source voltage is less than this threshold voltage or nearer to this threshold voltage, there will be a not complete formation of this channel. So that is called as weak inversion layer formation. So because of that, the current will flows. Okay, the amount of subthreshold current may become significant when the gate to source voltage is smaller than but very close to the threshold voltage of the device. That's what I have explained. Okay, the subthreshold leakage current can occur even when there is no switching activity in the circuit, and that component must be carefully considered for estimating the total power dissipation in the standby operation mode. In the standby operation mode means when there is no switching operations is taking place. Also, at that point, the subthreshold current will be flows, and the total subthreshold current ID subthreshold is equal to QDN WXC N naught by LB e power QT by KT e power Q by KT uh, A VGS plus B VDS. This is the subthreshold current what we have that gives the some part of the leakage current. Okay, now we'll go with the next one, that is the total power consumption. Okay, so what is the total power consumption? I told at the beginning, that is in the overview of power consumption. The total power consumption is due to the dynamic power consumption or switching power consumption, and another one is short circuit power consumption, leakage power consumption, and the final one is the fourth one is what? The static power consumption. Okay, so to calculate the total power consumption in CMOS digital circuit, we have to add all these contributions of all these four. Okay, that's why here I am adding that P total, the total power consumption is equal to alpha T C load VDD square multiply with F clock plus VDD multiply with I short circuit current plus I leakage current plus I static current. Okay, I short circuit current plus I leakage current plus I static current. So these two are what we have discussed here. Okay, I short circuit denotes the average short circuit current. I leakage denotes the reverse leakage and top threshold leakage current combinedly. Because this reverse leakage power consumption is contributed or is causes by 2 points. One is what? Reverse leakage current, another one is subthreshold current. That's why I leakage is equal to addition of both reverse leakage current and subthreshold leakage current. The final one is static current. Okay, what is the static current means here? The static current is nothing but the power consumption that is taking place due to the other circuits that are present on the chip except this CMOS digital circuits is called as what? The static power consumption. Okay, so here we have I static denotes the current components drawn from the power supply. Okay, so here out of this, the first term is nothing but what? The dynamic or switching power consumption. It is the major contribution to the total power consumption, and at the same time, if you observe here, I am multiplying the voltage with if you multiply voltage with the current, that will gives us what? The power. Okay, so here VD is the total voltage, that is power supply, and it is multiplied with I short circuit, I leakage, and I static currents. So we will get here the total power consumption taken place due to the short circuit current and due to the leakage current and due to the static power consumptions. Okay, this is what remaining three, and at the same time this one is the major contribution for this total power consumption. Okay, so this is about the power consumption that is taking place in CMOS digital circuits. Okay, so here under this what we have discussed is nothing but the reduction of switching power consumption. Next one is short circuit power consumption, and next one is the leakage power consumption. Under this leakage power consumption, we have seen about the threshold current and at the same time the reverse leakage current contribution to the leakage power consumption, and at the same time the final one is static power consumption. Okay, so and here we have the total power consumption equation, right? Thank you for watching. Subscribe our channel.